it's just like the first time I ever got it. I would never recommend it, by the way. Unless everybody thinks. Over 7 months ago. And my term slightly late. And then I never saw her. So. It depends on what we go. Like, it's just like my insurance will cover like 100%. So if we go through a house, so I signed after
When do we get those corrections, like, when do the corrections for the test show up on?
Oh, I haven't looked
Oh,
at
okay.
any
I
of
figured you
these.
got a lot of papers together.
Yeah, I
so
just
wanted to
haven't.
check. Okay,
Yeah, hopefully soon I'll be going through
yeah,
that.
and I sent you my resume and my,
Yeah, I saw that,
stuff,
so I'll send you back, yeah,
Okay, thank you.
PDF.
Yeah, I appreciate it.
Yeah, and they don't say anything about like sealing it or anything, or?
No, it didn't say anything, it just said upload file. So
Okay,
I was
yeah,
like, okay,
it's
I
a
can do
little
that.
open, but,
Yeah, that's
okay.
why I was like, I don't know, cause like RKC has like, that they have you just like do the link, but
Yeah.
CC's like, nope.
Yeah, that's funny. Morning. Morning. All right, so keep working on this problem. So we left off right last time on Q and what this was. So see if you can remember, right, just how do you set up the basic equilibrium expression, plugging in our values for Q, and then, right, comparing that, they gave us our equilibrium value. So, right, is Q smaller, larger? So give people a few more minutes to look at that and warm up on that. All right, so how's this problem looking? Does someone want to just give me the basic equilibrium expression? Like with the constants and stuff? Using our reactants and products? What's our K? Daniel, did you have this expression? Yeah. Can you just give us the general form for this reaction? So how would you write it with the variables?
The 0.355 divided by the other ones.
And then, but don't forget to square it, right?
Yeah, I squared the top one.
All right, so yeah, so we want ICL squared, and then you said over the reactants. So right, this is just our general form. And then, okay, let's plug in our values. And so again, right, they're giving us our snapshot here. And they're all in ATM. And so what do we get when we plug this in? And y'all can yell at me what you got as I typo everything again. All right, so I got 11. Is that what other people got? So some yes. We get that over there. All right, so then what does this tell us, this value? Is this less than, greater than, or equilibrium?
Less than.
So less than or equilibrium. And so what direction will the reaction proceed then?
To the right.
To the right, so in our forward direction, exactly. So right or forward. And again, just thinking about how we would apply this. All right, again, thinking back to our equilibrium, what we were doing there. So again, right, when we had set up this scenario, we had 0 of our products, right? So we knew it was going in the forward direction. But then later on, again, like we're seeing, there may be scenarios, right, where you have to figure out first, well, is it going to go forward? Is it going to go backwards? And then, of course, this dictates, our whole plus x, and in this case, obviously, plus 2x, since we're forming 2 equivalents. All right. Good. Any questions on that one?
The reaction quotient or snapshot, that's like you use the kind of given values at a very specific moment, and that gives you the direction that the reaction is.
Yeah, exactly. So yeah, if you can, again, if you're able to kind of sample it and take a snapshot, and then you can figure out which direction we're going.
Calculate K as well, right?
Well, we had to know the K for this one, right? So yeah, we can only calculate K once we're at equilibrium, but the Q is implying that we're not at equilibrium. And so then, now this is all the fancy words to go along with basically what we're just determining and saying. And so right, step 1 is going to be deciding which direction the reaction proceeds. So usually you'll either have all reactants, all products, and then obviously you'll be going the opposite way. But otherwise, right, if it gives you enough information, you can compare your Q to K. And then just like we did before with our Rice tables, then we can quantify things in terms of X, right, using our coefficients. And then, of course, again, right, whatever side it's proceeding is plus X. And so again, y'all saw, okay, it's going forward. That means we're going to be adding to our product side, subtraction from the reactant side in this case, and then solve for X. And so we'll be, again, kind of continuing to practice this solving for X thing. And so we'll look at when we can simplify too. And so again, just continuing this theme. So just repeat what our Rice table stands for. And so now let's practice again. And so again, this is just to emphasize our coefficients. So just looking at this example, again, proceeding to the right, assumably, then we're going to be losing minus x, since we have 1 equivalent here for our coefficient. Then we have 2b, so right, we'll be adding 2x there. All right, so let's try that again then with this reaction.
Does X represent the coefficient in front of the formula?
Yeah, because again, that's how many are being made, right? How many equivalent. All right, so let's look at our scenario. And looks pretty similar to what we've been looking at. So another dimerization reaction going back and forth. So we start with our dimer, N2O4, and then it splits into nitrogen dioxide, 2 equivalents of that. So see if you can just start setting up your rice table. See if you can get as far as the equilibrium concentration. But at the very least, right, just kind of start with it. Do your setup, right? You have your initial conditions. Which way is it going? And we'll go over it. So let's at least check in on our setup. I don't expect that anyone's done with the algebra if you've gotten that far. So I'll just rewrite our reaction, because again, I like making a yummy rice table instead of the cold ice table. And then, so what do we put for our initial conditions? So how many N2O4 do we have? Yeah. So we have none of our reactants. And then how much of our product? Someone, Kaden, you want to chime in?
2?
But what's the initial condition?
Oh. Sorry.
Yeah, so 0.1 molarity. And then what's our change here? So what's our dimer change, dinitrogen tetraoxide?
Plus X.
So plus X. And right, so that's a little unusual, but good, right? Because we know it's going to be going in the reverse direction. And we had none, so we have to be forming some. And then, so if this is plus X, what's this? And of course, pay attention to our coefficient. Yep, and then, but which direction then? So minus 2x, which again, a little unexpected, but from our starting conditions. And then equilibrium, so now we just, right, add our initial plus our change. So we have x, and then 0.100 minus 2x. And so now we want to plug this in. All right, so first, before I start taking off, did we all get to this point right here? This is kind of our checkpoint. All right, so any questions on that? And so now that we have our equilibrium values, right? And again, this should be similar to the lab in a lot of ways, except you had to solve for your equilibrium, right? So in our lab, we found X instead. So in this case, right, we need to find our equilibrium concentrations from our K. And so let's do that so we can set up our K expression. So I'm just writing, right, our generic form, products over reactants. And then we know that equals 0.36. And then we can plug these values in. So now we get, so plotting 0.1 minus 2x squared over x. So now we have something like this. And so now this is just algebra. So I'll just put algebra fun. So now I'm just rearranging. So I'm going to try to get everything in the quadratic form. And so now we need to distribute, so I won't write it like that. And so now we're just doing algebra. So first adder, inner, last. And then I'm just going to get everything on one side because I'm trying to go for the quadratic equation. So setting everything to 0.
Where did the X come from on the left side?
So we started here, so then I multiplied x, so then, yeah, so now we got 0.36x equals to this squared. And then write FOIL for this. And now I'm just trying to subtract minus 0.36x. So now quadratic form. And then, so do we remember the quadratic equations? Of course, right, it's in this ax squared plus bx plus c equals 0. And then, what's the magical formula?
B plus or minus the square root of x squared minus 4ac over 2a.
B squared minus 4ac. Yeah, and then make sure it's negative b. So negative b plus or minus square root b squared minus 4ac all over 2a. So now we can plug it in. Oops. So then we get something like this, so then we have to figure out which one is our real answer, right? So plugging it in to these and making sure that they give positive values. So let's see which one works. So let me try. So my only concern is if I add them, that might be too big of a number. So let's try that. So 0.76 plus 0.646 divided by 8. And so that gives me 0.175. But then the problem with that is if we try to plug it into here, right? So now this is x, so 0.1 minus 2 times x. Well, what's the problem with that? Yeah, so we can't have negative concentrations. Okay, so that's not the correct value. So let me take the minus then, because right, again, we have 2 possible answers, but only one is correct. And so let me do my subtraction. So minus 0.646 divided by 8. Okay, so now I get 0.014. I'll round it to 3. And now we can plug it in to kind of double check. So of course that works, but let's double check that the subtraction works, which I have a feeling it will. So times 2 and then 0.1 minus that. All right. So that gives us a positive value. And so now we're getting the equilibrium concentrations as well, solving. So now we can say, oops, sorry, that our equilibrium concentration of NO2, so again, I just plugged in this minus X, so 0.0715. And then the dimer concentration was just equal to X. So again, that was just the 0.0143 there. Questions on that one? And of course, you could always write double check yourself and plug it back in. Right? So, okay, this should match my equilibrium constant. So then you could just plug this value. Obviously, don't forget to square it. And again, right, just quick double check. That's squared divided by 0.0143. And so we get, right, our constant back out, so that looks good. There are values there. Questions on that one? All right, let's try another practice one. All right, so now it wants us to look at the same reaction at the same temperature. So all that means is, right, our equilibrium constant hasn't changed. But this time, now they're only giving us the reactant instead of the product. And so see if you can find our equilibrium concentrations then. And I can rewrite the Kc. And I'll rewrite the reaction in case we forgot. So 0.36. So see if you can set that up at least. It'd be good if you can go through the algebra. And we'll go over it.
the same constant?
Yeah, so same equilibrium constant since we're at the same temperature. Oh, let's give people a second. So let's start going through it. So they gave us our initial conditions. So it's just reactants now. So what was our change for our reactions? So what's our change for our reactants here?
0.025 minus x.
So just minus x for the change. So equilibrium 0.025 minus x. And then what's the change for our products?
Plus 2x.
So plus 2x, and then adding for equilibrium. So 2x. And so now this looks pretty similar, right? Just kind of different variables. Oh. And so we could rewrite our K, so 0.36, right, is equal to our product squared over reactants. And so then we can just plug in, so this is 2x squared then over 0.025 minus x equals 0.36. And so then just algebra at this point, so we got to distribute the 0.36. So 4x squared is equal to this. And then now I'm just going right for the quadratic form. So distributing first. And now I'm putting everything on the same side. Oops. Sorry, I just want to write it in the ax squared plus b form minus. And so now ready for quadratic. All right, so when you get down to it, I think it ends up something like this. And then what's our real answer? Because of course, right, you'll notice one of them is negative. And then
It's 0.020.
0.020. So do we get this for x? So excellent. So this is our real, well, real for x. And then now that we have x, we have to go back to plug it in to our equilibrium concentrations to find the answer. So then what do we get for our equilibrium concentration? So my NO2 is 2x, so what does that give me? 0.040. And then my dimer, so 0.025 minus x, what does that give us? 0.005. And then molarity for all of these. Excellent. Questions on that one?
I noticed the rice table, the signs get flipped, and compared to our last example, it's you have x on the left side and then 0.25 minus 2x on the right. I don't know, maybe I just did it backwards.
I guess
Does that change based on the direction of the reaction?
yeah, sorry, I didn't understand. Or could you repeat what you said?
So on the right you have plus 2x and minus x for the C quotient.
Yeah.
Initially, on the previous problem, it was negative 2x and then positive x.
Right, but then compare the difference, right? So in this case, we had started with all reactants, so we had to go backwards. So that's why it was minus x and plus x there, because we were consuming products, right, to make reactants. And then, yeah, in this case, we flipped it, right? So then we only had reactants. And so now we have to do minus x plus 2x. So yeah, direction does matter. And so let's try another one with that in mind. And so now we have to figure out our equilibrium values. And so we're doing this reaction again. And so now it tells us, okay, we have our iodine and chlorine to make iota chloride, just like before. Still the same Kp of 81.9. Then we have our initial conditions. So it looks like we're starting with 0.1 atm of all the gases. And so see if you can figure out the equilibrium pressures. So see if you can at least start it. So I'll let you look at it before I give hints. So before anybody takes off too far with their quadratic calculations, what do we have to do in this problem initially? So we can set up our table. So if we do that, okay, I have my reaction. So I2 here, and then 2 equivalents of that. And then, okay, I have my initial conditions. So 0.1, 0.1, 0.1. But then what do I do from here? How do I know my change, right? So what do we need to calculate?
We need to calculate the QC.
So we need our Q. Excellent. So, right, and this is a good example of, again, right, we have no idea what direction it's going to be going in. We have some amount of all of them, so it's not obvious. So let's calculate our Q. And, right, I'll just kind of rewrite, for completion's sake, our expression for equilibrium.
Is an equilibrium constant always expressed in terms of products over reactants?
Yeah. And so then let's plug in these values. Luckily, they're all 1 or 0.1. So 0.1 squared over 0.1 times 0.1. So what does that give you for 1? Yay. And so what does this tell us, though, about the direction?
It's gonna be going to the right.
So right, so forward direction, exactly. So we're not at our equilibrium. And so at that point, that's how we know our change. So then what's our change? So what's our iodine change? So minus X chlorine. So minus X, and then what's iota chloride? So plus 2X. And so then, once you're there, obviously you can write your new equilibrium for all of these. All right, so I'll give you at least another minute or so to get started on the algebra, and then we can finish walking through it together. And then if you have questions on the setup, let me know before, like I said, we take off on Algebra Road here. But just make sure you have the setup properly.
Scroll up a little bit. Where did you put one?
So then I'll just start kind of sketching it out, at least what I was doing, so you can follow along with your algebra fun. All right, how are we doing on the algebra? This one, the easiest thing, right, was to kind of take the square root, because you have these things squared and squared, so we can just get rid of the square, take the square root of 81.9. Then we're left with this, which is much more easy to solve, just algebraically yada, yada, yada. So, oh,
Why'd you set that equation to 81.9?
oh, because remember that was our KP, the equilibrium constant. Because remember, the Q is just to tell us what direction we're going. So, okay, that's how we knew we were going in the forward direction, so we could get the correct, whether it's minus or plus x. But then, once we get the equilibrium expression, right, then we have to reset it back to whatever the equilibrium constant is. So, yeah, so then it's just algebra fun at that point. And so when I got it, I got x of about 0.0729. And I just wanted to pause here and make sure. Yeah.
I'm a little confused and worried by the 11.05.
So just subtracting. So, right, you have this 9.05x. Did you get to this line? And then moving the x's, so 0.905 plus 2x gives me 11.05x. And then I move the 0.1, so subtract that. So now that leaves us with the 11.05x equals 0.805. And then x is this. Slight discrepancies are fine with rounding. And then, of course, plug back in, right? Still not done. So plug in. So I was just making sure we all got this x. So no other questions on kind of this? Always good to keep your algebra skills up. That's my other piece of advice. I started doing like a tiny bit of SAT math tutoring on the side, and all that made me realize is I forgot all my math tricks, but so I'm trying to refresh myself in general.
I got completely different values.
For what?
Can I see your rice table?
Yeah, so double check your rice table. Like I said, the math shortcut is just realizing we got a bunch of squares, so we can easily just square root that.
So,
Oh, yeah, how square?
I was gonna say, can you scroll a little down?
Oh, yeah.
I could do a bit lost. So I see that the square root, when you square rooted 81.9 to kind of get rid of the squares on the other side, it canceled out that denominator or one of those factors. And so I guess, is that like a pretty common like trait that you'll see in these types of problems where like, because in the rice table you have it being minus x, so it ends up being like a FOIL problem on that denominator. Is that pretty common to like see that pattern?
Yeah, so we're either going to see like tricks like that, or we'll look at one we can actually like simplify as well, so make like a little guesstimate.
Okay.
But yeah, that's kind of the
Is that
thought.
your final x value?
This was my final x value, but then I still haven't plugged in for the equilibrium. So right,
Okay.
yeah, is that what you got for x?
No,
I got 0.041.
but I also spoiled it all, and that's probably a dyslexia thing.
Yeah, double check. Oops, it would help if I knew how to divide. Yeah, because I still get that for my x value, or at least with some rounding potentially. And then, so once you get, right, your x value, we can plug it in to, of course, our equilibrium expressions. So luckily, I2 and chlorine have the same value. So I get 0.027 for about both of those. And again, we're in ATM for this problem. And so then our iota chloride value, let me plug that in still.
Is there any fundamental difference between how this is calculated versus regular equilibrium?
What do you mean?
Like in terms of like the functions you go through to find it, is it practically the same or is there?
Yeah, I mean, I don't know what the difference would be. This is, real world values. Like, yeah, the only, you could use a computer if you wanted to obviously solve this computationally. But yeah, I mean, this is how you can do experiments, right, in real life, set this up if you're trying to do this.
You're always doing the partial pressures in atmospheres? Or does it matter?
Yeah, yeah. So for these equilibrium constants, the partial pressures are always given in ATM.
What about like when you're doing solutions, is that in moles or mole?
Molarity, so it's always molarity. And so at some point we may have to, this is more like with the acid-base chapter, so we may have to do conversions where we'll have to go molarity moles, but then you always want to end up in back to molarity. And then if you wanted to double check, right, you want to feel extra good about yourself, just plug it in, make sure, right, double check, sanity check. And so then 0.2458 squared over, well, effectively 0.027 squared. And again, I'm just double checking that we're pretty close to our constant. And so yeah, a little discrepancy with rounding, but pretty close to 81. So that looks good there. All right, let's try to squeeze at least kind of one more problem in. And so the last bit is we can, of course, use approximations sometimes to simplify the math. This will become really useful with the next chapter, acids and bases. And so, of course, we may see some situations where our equilibrium constant is very small. And obviously, that would mean that the equilibrium favors the reactants. And so when we get this case, and obviously they've teased us what we have to check for, but basically 5%, that the change is less than 5%. And so we're saying, okay, when it's less than that, when that change is small, we can essentially assume that our equilibrium concentrations, again, assuming that minus x is small, that it's equal to our initial conditions. And so we'll practice that. And then you want to double check this approximation, so I'll kind of give you the hints of when it's probably safe to make that approximation. But then you do want to solve for x, double check it, right, and make sure that yes, it is less than 5%. Otherwise, if that's not true, then you'll have to solve with the quadratic formula or without making that assumption. So check that it is indeed true. So, right, if you want to make that approximation, do it. Like I said, just double check it. All right, so let's look at this. And so we're already kind of seeing our T's here. And so why we're already kind of knowing that it's a good thing to make an assumption is look at that equilibrium constant. So 10 to the minus 7, right, that's pretty small. So usually I say if you have like 10 to the minus 3 at least, but 10 to the minus 4 difference for sure. If you have, right, that much of a difference, then you can probably make a safe approximation. And so right away we can tell this is not very favored. Well, let's go ahead and set up our rice table and see how it's a little easier with our approximations. And so just like before, so reaction, two equivalents of our hydrogen sulfide is going to decompose into hydrogen and S2. And then, so initial conditions, looks like we don't have any products, but we do have 0.0125, so moles. And so watch out. So I'm going to change this because we want to be in molarity. So right, they're given moles, we're given our reaction vessel. So let's go ahead and change it to molarity to be consistent. So that's kind of tricky. All right, so now we have molarity. So 0.025 molarity. And so then write our change. So for this one, it's obvious what direction it's going in. It will go in the forward, right, albeit at a very small amount. But we'll still do our, so minus 2x plus x plus x. And so here's where, right, we can make our assumption, or we'll start to. And so let me just write it all out. So 0.25 minus 2x, so plus x plus x. And then let's just go ahead and plug this in to our Kc expression. So H2 squared. Oh, and this should have been, sorry, plus 2x. Plus 2x. So H2 squared times S2 over hydrogen sulfide squared. And so now just plugging everything in. So 2x squared over x is equal to 0.025 minus 2x squared is equal to our equilibrium value. And so now here's a good point to approximate, right? So this is looking pretty nasty. And so we can instead approximate. Again, we said this is going to be pretty small, so we can basically assume that it's 0.025. So, right, assume 5% or less than. And again, right, because it's to the -7 here, let me rewrite that up. I don't know why that came out funny. So 10 to the -7. So again, right, pretty small. And so now that helps us, at least with the math. So now that's 4x squared, so times x, so 4x to the third. So now I'm just algebra simplifying at this point. So 4x to the third over 0.025 now. And squared, almost forgot to square it, is equal to our constant. And so now we can just finish solving. So I'll just plug it into the calculator now. And so then I get this value for x. So x is 2.96 times 10 to the -4th. So did we get that? Or something at least close to that. And so then once we're here, right, we still want to double check our approximation, even though it's probably safe. So just double check our approximation. So dividing it right over the original amount over 0.025. Put it in terms of a percentage. So write 1%. So yes. Right, 1% is less than 5%, so yay. That was an okay approximation to do. And so now we can go ahead and find the equilibrium concentrations. And so you could go ahead, right, and plug this back into here. So 0.025 minus, what was our x again? 2.94. 2.9, what do we do? Oh, I forgot to do times 2 though. And so there's our equilibrium concentration for our hydrogen sulfide. So right, barely changed, which is what we expect. And then, so H2 was 2x. So 5.92 times 10 to the negative 4th molarity. And then S2 was just x. All right. Questions on that one? And then of course, right, you could double check yourself, plug it back in, make yourself feel good about it.
In your rice table, you have the reactions 2H2S to 2H2. And so it consumes 2, but it's still the same amount of hydrogen. So it's still 2x though? Or does that make sense where I'm confused at? So why isn't it a 1-to-1 ratio? Because you're consuming 2H2 and you're producing 2H2. So
But then your S2 is still x, right?
Yeah.
So you gotta-
That's the number of moles, so every time a molecule fractures, it doubles. So it doesn't necessarily have to like equal 0.
At least for the interchange portion of it.
Yeah.
Okay.
Other questions? So let's see, we're kind of, I'm surprised we're behind on lecture. Because we should technically stop for your quiz. Let's at least kind of look at this Le Chatelier's principle. And like all this is a fancy way of saying like which way the reaction is going to go. And a lot of it is a lot of text to kind of describe this. So let's at least look at the graphs, and then if we still have questions, we can continue next week. But kind of the idea and what it's saying is like, okay, we have a system at equilibrium. Again, we're looking at this dimerization reaction. And then it's asking us, okay, well, with Le Chatelier's principle, and again, you'll see this in lab. So I think the lab is valuable for Le Chatelier's principle. And so kind of the idea, and we can think about this in terms of lab real quick too, and kind of what you were trying to do with the high concentration of stuff. And so, right, you had this equilibrium reaction. So all Le Chatelier's principle is saying, and so in this case, right, let's look at our graph for a second. So we disturbed our equilibrium, so we added a bunch of product in this case, and all that's to say is, okay, yeah, we added a bunch of product, so now we have more product, right? We need to go backwards such that we get back to equilibrium. And that makes sense, right? So we have too much, so now it's going to reform the dimer. And then all it's saying is, okay, well now, right, our forward reaction rate is going to be, or not forward, backwards reaction rate in this case is going to be faster than our reverse until equilibrium, right, is reestablished and the rates are once again equal. And so kind of same thing with the lab, kind of depending what you did. So sometimes, right, you added a different source of iron 3, and then you saw how it got darker in theory, right? And so again, that just means you added more reactants. Now it has to make more products to get rid of those reactants. I think the other thing you could do in lab was you could remove like iron by complexing it with something, and so that would make it lighter. So taking, right, if you took iron out of the equation, and then of course, right, your dark complex would have to disassociate to compensate for that. So again, kind of same thing that's shown here. We were at equilibrium. We added a bunch of reactants. Obviously now the forward rate is going to increase until we're back at equilibrium. So that's all that's really saying. And then it's used in real life a lot with these condensation reactions. I just like mentioning this because this is pretty, it's relevant in organic chemistry. So let's just look at really quick what a Dean-Stark apparatus is. And so a condensation reaction is just a reaction that makes water, as you might guess. Let me just give the general form. So you have, you know, some sort of OH group reacting. So carboxylic acid with an alcohol is a common condensation reaction. And so the key is you lose water. And so kind of the problem, though, with these reactions is they can stall out if you have water. Well, the trick to get them to go forward is this Dean-Stark apparatus. If I can find a better picture. Let's see if this is a good picture. Oh, come on. I want a larger. All right, that was not useful. All right. All right, a little cartoony, but that's okay. So this is the Dean-Stark here, and it's basically a condenser with this little dropping burette such that you could release water, right? So that's kind of the theory. So you got your reaction going in here in some sort of organic solvent, and then it's getting rid of water though. And so, right, you're heating it up, refluxing it, condensing your reaction. That refluxing just means you're boiling it, and then you have a condenser on there to recondense it. And so all that does over time, and in this little cartoon they made the little drawing, but basically you got to pick the correct solvent, so you don't want to pick DCM that's going to be heavier than water. But most organic solvents are lighter, and so like ether would be floating on top here. Your water collects on bottom, and then you can drain out this water, and then right by Le Chatelet's principle, well, you remove some of your products, so now it's going to keep going forward to make more water, right, and continue the condensation reaction. So that's super useful, and sometimes these condensation reactions, I know from personal experience, can be slow, so like 2-3 days of refluxing, heating. So that's why you want to have a mechanism, right, to just keep driving them forward. Anyways, we should probably stop there so you can get to your quiz. We may look at this, like I said, on Monday, because the other thing that we kind of didn't really talk about was this endothermic, exothermic thing, which is covered in your lab. And basically, we want to treat heat. So this is a symbol for heat when chemists want to go shorthand. But we can treat heat like either a reactant or product. And so we can kind of discuss this in lab, but that was part of figuring out your little blood reaction is, was it exothermic, was it endothermic? And so we can talk about this, like I said, in the lab. All right, I'll probably stop there so you can have time to take your quiz. So we'll probably touch up on this, like I said, but read over the notes still, and we'll try to go over it next week. Or, like I said, you can ask me in lab about Le Chatelet's principle. All right, I will hand out the quiz, and then, of course, if you need to take your break, take a break. Oh, now I lost all the quizzes. And then, for this quiz, you might want the rate laws cheat sheet things. I have a few copies, so I'll leave them here. If I need to make more, then I'll do that. Two, that one. TV 1, 2, 3, that way. Here's 4. 6.
Is it not working?
Campbell's not here.
Where's Stephen?
His girlfriend's car is in the shop, so I have like a month and a half. So he has to go home and pick her up, go to stuff with his brother. And then Diamond just not been showing up to any classes. And then
Yeah, what's the,
I don't know about Diamond. Diamond just has not been showing up.
that's weird.
And then
Now I'm quite concerned, because Trinity is, I know.
and Trinity's
Trinity
building.
is communicating.
Yeah.
And
And then
No, actually,
Trinity's been sick. Now that she's been on the street, I haven't talked with her in a while.
yeah,
So.
I don't even have time to get on screen. Yeah, because she's friends with y'all, right?
Well, she's friends with me. I've known her for a long time.
Yeah,
but,
she's
yeah.
friends with Trinity.
She, when I message her, she doesn't respond or anything.